Swayam Prabha. Digital India. Educated India.
Today I'll talk about a very useful class of relations called partial orders, or posets, which stand for partially ordered sets. Okay. Let me start by reminding you of something we already talked about, namely transitive relations. So these are relations where if A is related to B and B is related to C, then A is related to C. Or alternately, if you can find a path from some node A to some node B, then you can find a direct edge from A to B in this relation. Okay. So here are some examples of transitive relations we already mentioned. This is a subset relation, less than or equal to or strictly less than, ancestor of, has the same last name as, equivalence, or congruence modulo some number. Okay, so these are all transitive relations. Let me add another dimension to this along the lines of being symmetric or antisymmetric. So again, this is something we already saw. So these are examples of symmetric relations where if A is related to B, then B is related to A, and these are antisymmetric relations where if A is related to B, then B cannot be related to A unless they are the same, right? So if A is an ancestor of B, and then B cannot be an ancestor of A. And if A is less than or equal to B, and if B is also less than or equal to A, then it has to be the case that A equals B. So I've started my examples along this axis. Now let me tell you an important property, prove to you an important property of transitive relations, which are also antisymmetric. So if you have both these properties, then that relation has to be what's called acyclic. It cannot have cycles. So you cannot go around following the edges in the direction of the arrow and get back to where you started from. Okay? That would be a cycle. Okay? So an acyclic relation cannot have cycles. So let's quickly prove this. So suppose somebody gives you a transitive antisymmetric relation and claims that it has a cycle. Okay? So suppose there is some cycle here shown here. Then what you do is you can follow the cycle starting from any node until you cover every other node just before you get back to this one, right? So you can find this sequence of edges or a path that takes you from the some node in the cycle all the way through all the other nodes and just before you get back to the same node again. Now this is a transitive relation, means that this path implies that there should be a direct edge from the starting node to this ending node. But that leaves you with a bidirectional edge, because in the this last edge is present in the cycle, and then we just now added a new edge which is in the opposite direction but connecting the same two nodes. So that gives you a bidirectional edge, and that contradicts the starting assumption that it is an antisymmetric relation. So an antisymmetric relation, antisymmetric transitive relation cannot have cycles. Okay. All right, so that's something useful to remember. Now let me bring in one more dimension to this. Again, there's something we already discussed, namely whether a relation is reflexive or irreflexive. These are two extremes. Reflexive means every element is comparable, is related to itself, and irreflexive means no element is related to itself. There's no self-reflexive. And in our examples, strictly less than is an irreflexive relation, ancestor of. So here my understanding is that you cannot be your own ancestor. Okay? So I'm calling calling A an ancestor of B only if A is not B themselves. It's somebody older than them, necessarily. So if A is an ancestor of B, then B cannot be an ancestor of A. So that's an irreflexive relation. And less than or equal to is a subset relation, they are all reflexive. A set is its own subset, and A is less than or equal to A for integers. Okay. On the other hand, these examples that we looked at has the same last name as or equivalence, congruence modulo number. They are both reflexive, and actually you can convince yourself that there is no relation, there is no interesting relation which is symmetric, no interesting transitive relation which is symmetric and irreflexive. It will have to be the empty relation. So that's something we can do as an example. Okay, so this is kind of what the landscape of transitive relations looks like in terms of these two axes of symmetry and reflexivity. Okay. And we already talked about this corner of this map. These are transitive relations which are both symmetric and reflexive. These are equivalence relations. And what we are going to talk about today are the things which occur on this side of the map. So at this corner, you have what you have are called partial orders. These are antisymmetric and reflexive transitive relations. Okay, so things like less than or equal to a subset. And you can also talk about things out here which are very similar to partial orders. They're called strict partial orders. The only difference is that instead of reflexivity, you have irreflexivity. Okay? You could also have a range of things in between here, which are neither reflexive nor irreflexive, but are antisymmetric transitive relations. So most of what you'll talk about, you'll talk mostly about partial orders, but many of these things translate to all these relations irrespective of the reflexivity property. Okay, so to summarize again, the definition of a partial order is a transitive antisymmetric reflexive relation, and we already saw some examples, less than or equal to for integers, subset relation. We shall shortly talk about this division relation. So A divides B, that's a transitive relation, which is also antisymmetric and reflexive. Containment for line segments, so you could think of the real line and consider intervals or segments there, and I would say A is contained in B, if it's a subset. So the interval A is a subset of the interval B, and you can convince yourself that it's also a partial order. Okay, and if you change the reflexivity property to irreflexive, you'll get strict partial orders. Okay, and from what we just now talked about, the acyclic property could be used as a substitute for antisymmetric property. So we saw that if it is, if it is a partial order, it is acyclic, and the converse also holds. If you have a transitive and reflexive relation, which is acyclic, then it also has to be antisymmetric, because if it is not antisymmetric, then you have a bidirectional edge, and the bidirectional edge corresponds to a cycle. You can go from A to B and come back from B to A. That's a short cycle. So being acyclic means you cannot have bidirectional edges either. Okay, so the antisymmetry property could be equivalently replaced by the acyclic property when you are talking about transitive relations. And again, you can attach either the reflexivity condition or a reflexivity condition, depending on whether you're talking about a partial order or a strict partial order. So here order refers to these properties, right? Being transitive and being acyclic. So if A is less than or equal to B, then and B is less than or equal to C, then A should be less than or equal to C. And if A is less than or equal to B, you cannot have B is less than or equal to A unless A equals B. Okay, so these are the transitivity and acyclic or antisymmetric properties. So that's what order refers to. Why partial? Because you would intuitively think of order as something which any two numbers can be ordered, right? If either A is less than or equal to B or B is less than or equal to A. But in a partial order, we want to emphasize that's not the case. There could be elements which are not comparable with each other. So two elements A and B such that neither A is related to B nor B is related to A. And concretely, the subset relation, you can very well have sets A and B such that neither A is a subset of B nor B is a subset of A. They could even have a non-empty intersection and still neither is a subset of the other. Okay. So a poset is just a convenient notation for a partial order, the relation, and the ground set on which it is defined. Okay, so technically a poset is a non-empty set and a partial order over that set. So you denote it by something like S comma a symbol for the partial order. So I'd use a symbol that looks like less than or equal to, and I would even often call it less than or equal to. It's the equal to part here is to emphasize that it's a reflexive relation. If I were writing a symbol for a strict partial order, I would choose a symbol that looks more like strictly less than rather than less than or equal to. Okay. So as an example, here is a poset S and subset relation. So S itself is a set of bunch of sets, right? So S1, S2, S3, S4, S5 are all sets of integers, and they are related by the subset relation which is shown here. So you can check this. Say S5 is contained in S1. So the set as a set containing 2 is a subset of the set 0, 1, 2, 3. So that's why you have an edge here. And all the edges are shown here. All the edges correspond to the subset relation. And you can check that there are no bidirectional edges. It is transitive. So if you have this path, say from S5 to S3 and S3 to S2, then you have the path S5 to S2. And it's reflexive, all the self-loops are there. Okay. So more generally, whenever you have a set of sets, you can define a poset using the subset relation over that set. So, and the fact that this is a poset, you can verify by checking that the set, basic set properties guarantee reflexivity, transitivity. Sorry, this should be a subset relation here, and this is antisymmetry. Right? If P is contained in Q and Q is contained in P, then P equals Q. My next example is where I actually use the divides symbol. So the set, there's an infinite poset. The ground set is set of all positive integers, and the relation is divide. So A divides B. That is the relation I'm talking about, and it's a poset because the divides is a partial order because it's reflexive. So A divides A. It's transitive. If A divides B and B divides C, then A divides C. And finally, it's antisymmetric. So if A divides B and B divides A, and there is something you can quickly verify, then A has to be equal to B among positive integers. Of course, if you allowed all integers, you can have a and b be negatives of each other, but among positive integers, this is a property you can quickly verify. So divisibility also, the relation also gives you a poset. And we'll actually use this as a running example, the divisibility poset, in the rest of this lecture. Okay, so once you have a poset, there are various interesting properties implied by this kind of combination of properties, right? Transitivity, being acyclic, and sometimes reflexivity. Okay, so the first property I want to mention is the notion of maximal or minimal element. Okay, so here is a definition. I would say that an element X in the ground set is maximal with respect to this, so in that poset, right? So X is a maximal element in the poset. If there is no Y, there is no other Y, there is no other element which is, I think of it as greater than or equal to X, right? So that's when X is maximal. So in this example, these green nodes here are the maximal elements. There is no node above them. There is no node such that this green node has an outgoing edge to it. Okay, so that's why it's these two are maximal elements. And similarly, you can define a minimal element. So a minimal element is one such that there is no other element which is less than or equal to it. So in this example, these are the two minimal elements. So note that they are of course being reflexive related to themselves. So that's why I excluded the element itself when requiring this condition that there is no Y such that Y is less than or equal to X. So there's no other Y such that Y is less than or equal to X. That's when X is called a minimal element. Okay, and maximal and minimal elements need not exist in a poset. For instance, if my poset is a set of all integers and the partial order is less than or equal to, then there is no smallest element or no biggest element in that. There's no element. For any element you pick, there is a smaller element, and for any element you pick, there is also larger element. Right? So there cannot be a maximal or minimal element in this poset. And sometimes you have posets where these things do exist, but they are not unique. For instance, if you took the divisibility poset, so it doesn't have any maximal element, so every element A has other elements B, multiples that, such that A divides B. So there is no maximal element, but there are minimal elements. But if you restrict yourself to integers which are strictly greater than 1, so if you allowed 1 also, 1 would be the minimal element, 1 divides everything and nothing else divides 1. But if I exclude 1 from my poset, then the minimal elements are all the prime numbers. Okay? The prime numbers are not divisible by anything other than 1, which are excluded, so they're not divisible by anything in the set. So there is no A such that A divides a prime number other than the prime number itself. And so these are all, every prime number is a minimal element. So clearly it's not a unique minimal element. Okay? So these maximal and minimal elements need not exist in a poset, and when they exist, there could be multiple. This example out here is also one where they do exist, but they are not unique. Okay. However, so they need not exist in general. However, if you consider a finite poset, then they do exist. Then there's at least one maximal and one minimal element. So it's a very useful property of a finite poset. How do we know it's true? Well, you have to prove this, and you can prove this by induction on the size of the ground set. So that's why it holds only for finite posets, right? So we're going to say for any poset of any integer size k, I'm going to show this holds, and your starting point would be k equal to 1. So remember, these are non-empty sets, and when you have only one element, that element is the minimal and maximal element, no matter what the relation is. And then you should try this yourself to prove that you can, given a poset of size k plus 1, you can talk about a poset of size k. You'd argue that the new set you construct is a poset, new relation is a poset of size k, and then make a case analysis to say, this one element that you excluded to get the smaller poset, either that is a minimal element, or the minimal element in the smaller poset remains a minimal element in the full poset. Okay, so I'll leave that as an exercise for you to work out for yourself. Not a very hard proof by induction. But once you do that, it's a very useful fact that you can use in proving other facts about finite posets. Okay, so you can use it only for finite posets, but you can use the fact that the finite poset has a minimal or maximal element, and use that in the induction step when you're doing other induction proofs. Okay. A couple of examples will occur shortly. Okay, so that is extremal elements, so maximal elements, minimal elements. There's also a notion of what you could think of as the maximum element or the minimum element, and the technical term we'd use is the greatest element. So an element is the greatest element in a poset if for every y it holds that y is less than or equal to x. Okay. And this includes y equal to x also, because I know x is less than or equal to x because I'm talking about a poset, not a strict poset. Okay, so this is the definition of a greatest element in a poset, an element x such that for every y is less than or equal to x. And similarly, the least element would be an x such that for every y, x is less than or equal to 1. Okay. Again, I'm saying less than or equal to, but it's whatever the relation is here, whatever the partial order is. And the greatest element, just like maximal and minimal elements, need not exist. Even, in fact, they need not exist even in a finite poset, right? So here, there is no greatest element. If it were to exist, it would have been one of these maximal elements, but since there are two maximal elements, neither of them can be the greatest element. Right? To be the greatest element, you'll have to be greater than or equal to the other element also, but they are incomparable, so neither of them is the greatest element. Similarly, neither of these are the least element. However, if they do exist, if a greatest element exists, then it has to be the unique greatest element. You cannot have two distinct greatest elements, because they cannot, both have this required relation without violating the anti-symmetry property. Okay, so in a poset, the greatest or the least elements need not exist, but if one exists, then it is unique. To see some of the structure of a poset, it's useful to look at some other relations that you can derive from a poset. So consider partial order, which I denote again by this symbol less than or equal to. I can define a strict partial order from that simply by removing all the reflexive relations, all the self loops. So what I would be left with is this relation, which is defined as same as the original given relation, except an element is not related to itself. Okay. So this relation is called the reflexive reduction of the original relation. And what that means is that if it has all the information about the original reduction, but it's itself irreflexive. But I can recover the original relation by taking the reflexive closure of this new relation. Okay, so the new relation is something which is by itself irreflexive. So it's a little simpler. It has fewer related pairs. In particular, it doesn't have the self loops. On the other hand, it has all the information about the original relation. You can recover the original relation from it by taking the reflexive closure. Okay, so that reflexive reduction is just a fancy name for removing all the self loops. I could also define something called a transitive reduction, which may be a little less obvious. So this is not a transitive relation anymore, the new relation that I defined. In fact, it's trying to be just the opposite of being transitive. So what it says is that if A is related to B, then you don't want it to be the case that there is a path from A to B other than this edge. Okay, so and further, importantly, this new relation still has information about the original relation. You can recover the original relation by taking a transitive closure of this new relation. Okay? So here, this is the transitive closure of the new relation. That will be the original relation. And you don't want, but you don't want it to be the case that there is some other node A that you could pass through in the original relation. So there's a path, there's an edge in the original relation means it's a path in the new relation, right? Because the original relation is the transitive closure of the new relation. So there's a path in the new relation that passes through some edge, some node M other than A and B, and still goes from A to B. If that is the case, so if there is such an M, you don't want this edge. You put in an edge only if there is no such M. Okay, so this is a definition of what a transitive reduction is. So it's a relation whose transitive closure is the original relation, but in some sense it is the very opposite of being transitive itself. There is a direct edge only if there is no other path from A to B. Now, I defined it as the transitive reduction. It's not clear, it's unique, but actually there's something you can prove that if there is a transitive reduction, it's unique, but it's not even clear if it exists. However, for finite posets, you can show that it exists. In fact, just define the relation using this condition here. So it consists of all the pairs AB, so all the edges in the original relation, as long as they do not have this issue that there is some other path in the original relation connecting A and B. So just delete all those edges. Whatever you are left with, define that as the new relation, and you can prove that if the poset is finite, okay, so this is going to be a proof for induction, which applies only to finite posets, that this resulting new relation will satisfy this property. So it's clear that it will satisfy the second property, that is by definition. What's not clear is that the transitive closure of this will actually get back all the original edges. Okay? So that's something you can prove by induction. I'll leave that as an exercise. And again, as we mentioned, for finite posets, to prove something by induction, you can use the fact that it has a minimal or maximal element. However, if you go beyond finite posets, this is no longer guaranteed to work. In fact, think of this example of real numbers. Okay, so this relation which says I can have A related to B only if there is no intermediate M such that A is less than or equal to M and M is less than or equal to B. So some real number M between A and B. Here between means in the standard notion of less than or equal to for real numbers, right? If that's how we want to define this new relation, well then no two distinct numbers can be related to each other because there is a real number between any two distinct real numbers. For instance, take their average. Right? So it's what you would be left with, according to this definition, would be the equality relation. So there cannot, and if at all any relation was going to be the transitive reduction, it had to satisfy this condition. So it had to be this, but its transitive closure doesn't give the original relation back. Since there are no edges other than self-loops, the transitive closure will just be the same equality relation. Okay, so transitive reduction, it's something that's well defined for finite posets and may or may not be well defined for infinite posets. So let me give an example. Let's go back to our divisibility poset as the running example. Now this is an infinite poset, but it so happens that here we will have both a transitive reduction and reflexive reduction. So reflexive reduction is simple enough. Just just consider that everything is not related. No element is related to itself. For seeing what the transitive reduction is, consider this poset, which is defined on the same ground set. Okay, actually this relation is both the transitive, I'm defining it to be not reflexive and not transitive. So here is a relation. I define A is related to B if and only if B divided by A has to be an integer and it has to be a prime number. Okay. So first of all, just because it has to be an integer, we need A divides B. So this relation is a sub-relation of this. So A is related to B according to this new relation, only if A is related to B according to the original relation. And further, it's a strictly smaller relation. So B divided by A has to be a prime number now for it to be considered for A to be related to B. Okay. So here is the illustration. So this is the graph. I've listed all the integers 1, 2, 3, 4, 5, 6. It goes all the way to infinity. And I've drawn it in such a way that I'm not drawing the arrows from 1 to 2. So 1 is related to 2 because 2 divided by 1 is a prime number. 2 is related to 4. 4 divided by 2 is a prime number. Okay, I've not drawn the arrows. Instead, I've drawn it a little upwards so that the arrows are meant to be going up in each of these little edges. And I have 3 to 6 there is an edge, 3 to 9 there is an edge, but 1 to 9 there is no edge because 9 divided by 1 is not a prime number. Similarly, say 1 to 6 there is no edge. Okay, but instead I have edges 1 to 3 and 3 to 6. I'm claiming that if I took the transitive closure of this new relation, you would actually get the original relation. So if, even if I found, if I took B and A such that B divided by A is not a prime, I could consider that B divided by A as a product of a bunch of prime numbers, and then I can use that to find a path in this new relation connecting A to B. So if I took the transitive closure of this new relation, I would have edges like say 2 to 12, right? Because I'll have this 2, 6, 12, and now there'll be in the transitive closure, there'll be a direct edge from 2 to 12. So whenever there is whenever it's a case that A divides B, In the new relation, there may not be an edge from A to B, but there will be a sequence of edges corresponding to prime factor, multiplying by one prime number at a time. That takes you from A to B. Okay? So you can verify that if I take the transitive closure and the reflexive closure, what I'll be left with would be the original, will be the divide separation. And in fact, this is the smallest such relation, in the sense that there is a transitive and reflexive reduction of divide. So the way I've defined it is, first take the reflexive reduction and then take the transitive reduction, and you will get back exactly this relation. Okay? So again, there's something you should verify using the properties of prime numbers. Okay, so so this is an example where I do have transitive reduction, even though it's an infinite set. Okay? That just happens to be the property of prime factorization, how it works. Now, this diagram that you see here is a much simpler, is a less cluttered picture than if I were to draw the actual graph of the divides relation, right? And that is because I, say in the divides relation, I will need an edge from 2 to 12. Now, you can still see there should be an edge from 2 to 12 because there's a path from 2 to 12, but I don't need to draw the edge itself. Okay? So this idea that, to represent poset or a partial order, you can simply look at the transitive reduction, its transitive reduction, or more precisely, the transitive reduction of its reflexive reduction. So you remove the self loops and you remove any edge that can be inferred from other edges. Right? So if you remove all that, what you'd be left with is a transitive reduction, if it exists. And you can just look at the graph for that. Okay? For finite posets, it always exists. For infinite posets, it may or may not exist. And when it exists, you can use that diagram, typically for finite posets, because that's when you draw diagrams. You can use that diagram, use that graph for the transitive and reflexive reduction of the original relation as the as a representation of the original relation. Okay? And in fact, this is how we'll do it. We'll drop the arrowheads. Instead, we'll have edges pointing upwards. So the arrowheads are implicit in this diagram. So this kind of a diagram is called a Hasse diagram, and you'll see that used for posets often. In fact, here is a simple example to kind of convince you it's a good idea. So this is the poset we saw from a few slides back, and if you look at its Hasse diagram, it's much less cluttered. You can get rid of all the self loops, and you can also get rid of edges like, say, these, right? These edges here or this edge here, because they're all implied by various other paths. Okay, so it's much clearer to see what's going on if you look at the Hasse diagram. Okay, now let me go back to this concept we introduced a little while back of maximal elements and greatest and least elements. But redo that now for not the entire set, but possibly a subset of T. This is actually nothing different. It's exactly what we had earlier. It's just that everywhere, instead of saying maximal element in S, I'm saying maximal element in T. Essentially, I'm just looking at a new poset obtained by. So, given any poset, I can take any arbitrary subset of the ground set, and I get a poset corresponding to that subset. Right? So, this is all just definitions of extremal and greatest and least elements defined for that subset. I've written the definition of maximal and minimal elements a little differently here. It's saying the same thing. now the way I've written it, it says, so for x to be a maximal element, well, if there is some y, whenever there is a y such that x is less than or equal to y, that's because that y is equal to x. Okay? Otherwise, you cannot have it. If y is not equal to x, you cannot have x less than or equal to y. Similarly for the node. Okay, so this is still what we already defined. What I want to define now is a notion of a bounding element. So I'll define an upper bound for the subset T as an element which is possibly outside of T. It's an element in this S, such that it's almost the same definition as the greatest element in T, right? It needs to be an element for X to be an upper bound for T. It has to be the case that every Y in T satisfies Y less than or equal to X. Okay, so X has to dominate, or X has to be above every element. It could be, X could be in the set T, in which case it would also be the greatest element, but X could also be outside the set T. Okay, so there could be many upper bounds for a set T. If T has the greatest element, that would be one of the upper bounds, but there could be other upper bounds, or even if T doesn't have a greatest element, there could be upper bounds for T outside of T, so in S. And similarly, lower bounds. So an element is a lower bound if a lower bound for T if every element in T satisfies that, every element Y in T satisfies that, X is less than or equal to Y.